Welcome to this presentation on fields and their consequences. Fields are regions of space where objects experience a force without needing direct contact. In A-level physics, we study gravitational, electric, and magnetic fields and how they affect objects and particles. Fields and their consequences in A-level physics, the concept of a field and action at a distance. A field is defined as a region of space in which a particle with a particular property, such as mass or charge, experiences a force. This idea allows physicists to move away from the outdated concept of action at a distance and instead describe interactions using measurable field quantities. For example, gravitational fields explain planetary motion and satellite orbits, electric fields underpin capacitors and electronic devices, and magnetic fields are essential to motors, generators, and transformers. A key consequence of fields is that they store energy. Gravitational fields store gravitational potential energy, electric fields store electric potential energy, and magnetic fields store magnetic energy. A field is a conceptual and mathematical model used in physics to describe how objects interact without physical contact. In classical mechanics, forces such as gravity appeared to act instantaneously across empty space, leading to the idea of action at a distance. Modern physics replaces this with the concept of a field filling the space around an object. For example, a mass creates a gravitational field around it, and any other mass placed within that region experiences a force. Gravitational field strength and definition, Newton's law of gravitation and the inverse square law, gravitational field lines and visualization, gravitational potential and potential energy. Gravitational field strength is represented by the symbol G and has units of n kg to the power of 1. Mathematically, it is given by G equals F or m. Near the Earth's surface, G is approximately 9.81 n kg to the power of 1, meaning that every kilogram of mass experiences a gravitational force of about 9.81 n. Gravitational field strength is a vector quantity, having both magnitude and direction, with the direction always pointing towards the center of mass causing the field. This explains why objects fall towards the Earth when released. Away from the Earth's surface, gravitational field strength varies with distance, decreasing as distance from the center of the Earth increases. Newton's law of gravitation states that any two-point masses attract each other with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. The equation is F equals gmm over r squared, where g is the gravitational constant. The inverse square nature of this relationship is particularly important, as it shows that doubling the distance from the mass reduces the field strength to 1/4 of its original value. Gravitational field lines represent the direction and relative strength of a gravitational field. By convention, gravitational field lines point towards the mass that creates the field, since gravity is always attractive. The density of the field lines indicates the strength of the field, with lines closer together representing stronger gravitational fields. Around a point mass, such as a planet, the field lines are radial and evenly spaced in angle, illustrating spherical symmetry. Gravitational potential is defined as the work done per unit mass in bringing a small test mass from infinity to a point in a gravitational field. It is denoted by V and measured in J kg to the power of 1. For a point mass, gravitational potential is given by V equals gm/r, where the negative sign indicates that work is done against the gravitational attraction. Gravitational potential energy can then be calculated using U equals mv, linking potential directly to energy. One key consequence of this approach is that it simplifies the analysis of systems involving large changes in distance, such as satellites moving in elliptical orbits. Electric field strength and definition, electric field patterns and field lines, Coulomb's law and inverse square behavior, electric potential, potential energy and capacitors. Electric field strength is defined as the force per unit positive charge experienced by a small test charge placed at a point in an electric field. It is given by the equation E equals F over Q and has units of n c to the power of 1 or V m to the power of 1. Electric field strength is a vector quantity, with its direction defined as the direction of the force on a positive test charge. Electric fields can be produced by charged objects and exist even when no test charge is present. One major consequence of electric fields is that they explain electrostatic forces without requiring direct contact, similar to gravitational fields but typically much stronger. Electric field patterns are represented using electric field lines, which show the direction and relative strength of an electric field. By convention, electric field lines point away from positive charges and towards negative charges, indicating the direction of force on a positive test charge. The density of field lines represents the magnitude of the electric field, with closer lines indicating stronger fields. Coulomb's law describes the force between two-point charges. It states that the electrostatic force between two charges is proportional to the product of the charges and inversely proportional to the square of the distance between them. The equation is F equals QQ, 4R squared. This law demonstrates that electric forces, like gravitational forces, follow an inverse square relationship. One important consequence is that electric forces decrease rapidly with increasing distance, but they are significantly stronger than gravitational forces for particles of comparable size. Electric potential is defined as the work done per unit charge in bringing a small positive test charge from infinity to a point in an electric field. It is measured in volts, V, where 1V equals 1J c to the power of 1. Electric potential energy can be calculated using U equals QV, linking energy changes directly to potential differences. One key consequence of electric potential is its role in capacitors, which store energy in electric fields. For a parallel plate capacitor, the electric field is uniform and the potential difference is related to field strength by E equals Vd. Magnetic fields and field patterns, forces on moving charges and current-carrying conductors, electromagnetic induction, and changing field. Magnetic fields are regions where magnetic materials, moving charges, or current-carrying conductors experience a force. Magnetic field lines form closed loops, unlike gravitational or electric field lines, and by convention they point from the North Pole to the South Pole outside a magnet. The density of magnetic field lines represents field strength, with closer lines indicating stronger fields. Magnetic fields are produced not only by permanent magnets but also by electric currents, linking magnetism closely to electricity. Field patterns around current-carrying conductors are particularly important, as they explain how forces arise in motors and other devices. Magnetic fields exert forces on moving charges and current-carrying conductors and is described using the equation F equals BQV sin for a single moving charge, and F equals BIL sin for a straight conductor of length L carrying current I. Here, B represents magnetic flux density, measured in Tesla, T. Force is greatest when the motion or current is perpendicular to the magnetic field and zero when it is parallel. Fleming's left-hand rule is used to determine the direction of the force, linking field direction, current direction, and force direction. Electromagnetic induction occurs when a changing magnetic field induces an electromotive force, EMF, in a conductor. It shows how changing fields can transfer energy. Faraday's law states that the induced EMF is proportional to the rate of change of magnetic flux linkage. Lenz's law then determines the direction of the induced EMF, ensuring conservation of energy. Comparing gravitational, electric, and magnetic fields, graphs, calculations and required practical skills, summary and key exam takeaways. Gravitational and electric fields both follow inverse square laws and can be described using similar mathematical structures, such as field strength and potential. However, gravitational fields are always attractive and depend on mass, whereas electric fields can be attractive or repulsive and depend on charge. Magnetic fields differ in that they are produced by moving charges or magnets and act only on moving charges or magnetic materials. Electric forces are much stronger than gravitational forces at the particle level, but gravitational forces dominate on astronomical scales because mass is always positive. Strong mathematical and practical skills are essential for success. Students must be able to interpret and sketch graphs such as force against distance, field strength against distance, and potential against distance. Recognizing inverse square relationships and understanding gradients as physical quantities, such as field strength, is particularly important. Calculations often involve rearranging equations, using standard form and applying appropriate units. Practical skills include understanding experiments that demonstrate field patterns, such as using iron filings or plotting equipotential lines. In this topic, we have explored gravitational, electric, and magnetic fields. Understanding fields allows us to explain forces acting at a distance and many important technologies around us. Thank you for watching.